Morning to all. I am Daniel Biju Eazon, Assistant Professor, Vedavyasa Institute of Technology, and in this episode of Techtalk, I am here to present Delhi air pollution, cause, effect, and mitigation. This presentation is based on the comprehensive study on air pollution and greenhouse gases in Delhi by IIT Kanpur, Delhi Pollution Control Committee, and Department of Environment, NCT, Delhi in 2015. The objectives of the studies were to identify and inventorize emission sources, chemical septation of particulate matter, perform receptor modeling, project emission inventories using mathematical modeling, identification of various control options and assessment of their efficacies, selection of best control option from the developed controlled scenarios. The components of study were air quality measurements, emission inventory, air quality modeling, control options, and action plan. Air quality measurement. The air quality sites were categorized based on predominant land use pattern. 6 sites were selected. PM10 was studied, PM2.5 was studied, SO2, NO2, carbon monoxide, organic carbon, elemental carbon, ions, elements, and polyaromatic hydrocarbons were considered for sampling and measurements. The air quality sampling was conducted for 2 seasons, winter 2013-14 and summer 2014. PM10, the study showed that the overall concentration of PM10 in summer season is over 500 micrograms per meter cube against the acceptable level of 100 micrograms per meter cube. Soil and road dust and airborne fly ash are the major source of PM10 pollution in summer. Atmosphere looks whitish to grayish, which can be attributed to the presence of large amount of fly ash and dust particles in the atmosphere. The overall average concentration of PM10 in winter season is around 600 micrograms per meter cube against acceptable level of 100 micrograms per meter cube. Soil and road dust and airborne fly ash have reduced significantly in PM10 in winter. Burning of municipal solid waste has the relatively higher contribution in winter season. For PM2.5, the overall average concentration of PM2.5 in summer season is around 300 micrograms per meter cube against the acceptable level of 60 micrograms per meter cube. Soil and road dust and airborne fly ash is significant source of PM2.5 pollution in summer. Burning of municipal solid waste has had a relatively higher contribution to PM2.5 than to PM10. The overall average concentration of PM2.5 in winter is 375 micrograms per meter cube against the acceptable level of 60 micrograms per meter cube. The Cl minus content in PM2.5 winter is also consistent at 7%, which is an indicator of municipal solid waste burning, which is relatively higher in winter than in summer. It was observed that in winter the atmosphere looks very hazy and characterized by smoky and unhealthy air. The consistent and major contributors appear to be secondary particles and combustion related emissions with modest contribution of burning of municipal solid waste. Potassium, NOx and SOx. The highest potassium levels of around 15 micrograms per meter cube were seen in the beginning of the November and early winter, perhaps due to the crop residue burning in Punjab and Haryana. Potassium levels stabilize around 4 micrograms per meter cube, which is also high in the rest of the winter months, suggesting the biomass burning is prevalent throughout the winter locally and regionally. NO2 levels in winter are high and they do exceed the national air quality standard of 80 micrograms per meter cube at a few locations. In addition, high levels of NO2 are expected to undergo chemical transformation to form fine secondary particles in form of nitrates, adding to high levels of existing PM10 and PM2.5. SO2 levels in cities were well within the air quality standard. The general inferences from the studies was the level of PM10 and PM2.5 and NO2 are statistically higher in winter months than in summer months, but by about 25 to 30%. In general, the pollution levels in the ambient air, barring traffic intersections, are uniform across the city, suggesting the entire city is stressed under high pollution. The CO2 levels are well within the ambient air quality standards during the summer. The concentration exceeds the standards during peak traffic hours in winter. In broad sense, air is more toxic in winter than in summer as it contains much larger contribution of combustion products in winter than in summer months. During Diwali days, PM levels nearly double from the average level of organic content of PM increase more than twice. It is noteworthy that levels of potassium and barium, the major components of firecrackers, can increase by about 10 times. The emission inventory was created with the air quality data which was produced. The overall baseline emission inventory for the entire city was developed for the period of November 2013 to June 2014. The pollutant-wise contribution were created and spatial distribution of pollutant emissions from all sources were mapped. PM10 sources in the different sources emission load from the city of Delhi. We can see that 56% of PM10 emission load is from the road dust. Again, you can see 10% from the concrete batching, 10% from the industrial stacks can be or is also attributed as the PM10 emission load. For PM 2.5 emission load from different sources in city of Delhi, 38% is from the road dust, 11% is from the industrial stack, 20% is from municipal solid waste burning, and 12% is from medical incinerators. The NOx emissions from different sources in the city of Delhi shows that 52% of the NOx emission is from the industrial stack and 36% is from the vehicles. This is the spatial distribution of PM10, PM2.5 and NOx emissions in the city of Delhi. We can see that the northeast and eastern part of the Delhi are most affected by air pollution. The air quality modeling was then created, and for PM2.5 in winter, we can see 25% of the PM2.5 is produced by vehicles, 30% is produced by secondary particles, which are combination of particles in the lower level of atmosphere, and 26% of PM2.5 is attributed from the biomass burning. In summer season, PM2.5 predominantly is from the road and soil and road dust, that is of about 28%. Coal and fly ash burning residue is about 26%. Secondary particles is only 15% and biomass burning is 12%. Vehicles attribute 9% and solid waste burning 7%. The control options were found for different areas. For hotels and restaurants, coal has to be changed to gas. Domestic sector, LPG distribution was considered as a control option. Coal and fly ash, the resuspension of the coal and fly ash in the industrial sector section itself is a control option produced. The municipal solid waste burning, it is better to burn it in an energy developing scenario where waste is converted into energy than rather burned in open areas. Construction and demolition work, waste management can reduce the airborne particulates. The ready mix concrete batching control at production area itself should be implemented as a control option. Vehicular pollution, BS6 implementation is a option to control the emissions from the vehicles. Soil and road dust sweeping and vegetation can provide a cover against the soil and road dust, which is a major component of both PM10, PM2.5. The industries and diesel generators has to go into LDO instead of HSD. Secondary particulates, desoxing of these power plants are required. Secondary organic aerosols, vapor recovery in petrol pumps are a control option. Biomass burning, alternative to crop residue burning, are to be taken into control. So the action plan was taken for 2016 to 2023 in this study, and with this with the action plan which is produced in the study, almost 100% of the existing pollution can be removed. The first option is to stop use of coal in hotels and restaurants. There are almost 9,000 hotels in the study area which used coal for their barbecues. So LPG should be provided to all the citizens so that they will stop biomass burning in the winter season for heat and for cooking. Stop municipal solid waste burning, improve collection and disposal through landfill and waste to energy plants. Construction and demolition, vertical cover in the construction area with fine screens, handling and storage of raw material should be implemented, completely covering the materials such as sand, cement, etc. Water spray and windbreakers and store water waste inside premise with proper cover. At the time of on-road movement of construction material, it should be fully covered. For concrete batching, water spray, windbreakers, back filters at silos, enclosures, hoods, curtains, telescopic chutes, cover transfer points and conveyor belts all can help in reducing the emission. Road dust, vacuum sweeping of the major roads 4 times a month is recommended. Carpeting of the shoulders, mechanical sweeping and water washing also will reduce the road dust. Soil dust, planting small shrubs, perennial forages, grass covers will stop the rising of soil dust when there is wind. So for vehicles, the action plan recommended retrofitment of diesel particulate filter, implement of BS6 for all vehicles including heavy duty vehicles, non-CNG buses and trucks were to be converted to BS6, and light vehicles should be converted also into BS6. Inspection and maintenance of vehicle must be implemented. Ultra low sulfur fuel less than 10 ppm should be BS6 compliant. Two-wheelers with multi-point injection system or equivalent should be implemented. Electric bar hybrid vehicles for 2% for at least 2% of two-wheelers, 10% of three-wheelers and 2% of four-wheelers, and all the new residential and commercial buildings should have charging facilities for electric vehicles. So the industrial and diesel generator set should have reduced sulfur components in industrial fuel to less than 500 ppm. Minimize uses, uninterrupted power supply should be provided so that DG sets are not used. Banning 2 kilowatt ampere or smaller DG sets will also reduce the emissions. Desoxing and denoxing the power plant within 300 kilometers of radius of Delhi was also considered as an action plan in this study. Controlling evaporative losses during fuel unloading and refueling through vapor recovery systems in petrol pumps will reduce the vapor emissions from the petrol pumps, and that was recommended in the action plan. Managing crop residue burning in Haryana, Punjab and other local biomass burning potential alternatives, energy production, biogas generators, commercial feedstock for cattle, composting, conversion in biochar, raw material for industries, windbreakers, water supply, water spraying, plantation, reclamation. All those were suggested as action plan for the reduction of emissions from the individual areas. Thank you.